That's right, folks. It's time for Solar Energy Fundamentals, video number 5. Let's talk about shading. Shading is something that we try to avoid with solar systems, especially because we have solar cells at least, and a lot of times strings, that are connected together in series. With series connections, shading is not always proportional. That means that you could perhaps shade 10% of a module and lose all of that module's production. It depends on the module. It can get kind of advanced in the explanation, but let's do it. This is a picture right here that I took of a PV array in New Jersey. We call this Mars, New Jersey, because it's the M&M's people, the Mars Candy Bars crew. This particular array is a first solar array, so this is thin film. It doesn't have those regular square or square with rounded corner solar cells. It has many thin stripes, and they put these thin stripes up and down like this. So with this type of solar module, you can shade the bottom of it, and it actually is proportional. So this shadow is not as bad with a thin film array as it would be with crystalline silicon solar. This particular type of thin film is called cadmium telluride. We're going to hit this in the next module when we talk about PV module fundamentals. What we have here is called interrow shading, and that's shading between rows. This was a winter day in the morning. Remember, it was very cold, and we had this row shading this row. There's two different ways that we could get rid of this shading. We could decrease the tilt angle, or we could move the rows further apart. Perhaps they didn't do that because it was an engineering decision, and the engineers decided that they could do with those winter morning losses. They might not have had enough real estate to fit everything if they spread the rows further apart, and if they tilted it less, then they would have lost more production for not being tilted at the sun as much. You can see that we have steel driven into the ground. It's driven into the ground like a nail. It's called a pile. Pile driving is the main way that utility scale solar farms are installed. These particular modules here don't have frames, so they're frameless. They're more likely to break. They don't have to pay for frames. They have to have special clamps with gaskets, and sometimes they're called laminates because they're made with a thin film laminating process, substrate on glass. This device right here is called the Solar Pathfinder. This has been around for a long time, since before the digital age took over solar. It's a neat thing. It's very intuitive. I have a few of them. I travel around the world with them. People still use them. What we have here is a reflective dome that's made out of plastic, and then we put that over a piece of paper that has a sun chart path for the particular latitude range that you're in. Then we have a compass, so we orient this in the right way. But along with azimuth, we also have to keep it level, and right here we have a bubble level. What the person in this picture is doing right now is they are holding it level, pointing it south, and snapping a picture so they can analyze the data later. Now you can see right here where the tree line and the house line interrupts the sun path at different times of the day. It's possible that you could have a PVA exam question that had something on it like this, and it would say, in June, what time does the sun come up behind the tree? And that would be about 7:45 a.m. solar time. We can also see that there's all these little numbers here, and if you added each number up for every month, it would equal 100 for 100%. So we could take these numbers, 2 plus 2 is 4, plus 1 is 5, plus 1 is 6, and we could say that we lost 6% of our June energy due to that tree. Darn tree. In different latitudes, we would have different sun path charts. Once you got to the tropics, the sun path would start to go straight overhead, which would be right over the middle of this reflective dome, right where the bubble level is. And since this is using a magnetic compass, you would also adjust it for magnetic declination. This will spin. You spin it counterclockwise if you're on the western part of the United States, and you spin it clockwise if you're on the eastern part of North America. If you're in the middle, say on the Mississippi, you don't have to spin it at all. Here's the sun chart that goes into the Solar Pathfinder. It used to be, before everyone was carrying a camera around in their pocket, that they would use a chalk pencil and they would draw a line to outline where the sun would be shaded throughout the solar window. The solar window is all the places throughout the year where there might be sun. We can see in this picture that December is getting no sun. This would not be a good location for an off-grid system, because for an off-grid system, this person is getting no direct sunlight in December, which would not be too good unless you're a snowbird. That means taking off for the cold months, going south. You can see up here, these are the magnetic declination numbers. Also with the Solar Pathfinder, you can take a picture, click your mouse around where all the shading objects are. You get something like this, import it into the Solar Pathfinder Assistant software, and it would generate a report to give you a hard number that says what percentage shading that you had for the year. Neat stuff. And you know what? It doesn't even take batteries. So I would say that that reflection there is solar powered. Here's some slides that I got from Solmetric. They make another shading device that competes with Solar Pathfinder. This is an older array. You can see that it has polycrystalline silicon where the poly part really stands out. It's reflecting light in different directions. Nowadays with polycrystalline silicon, they're better at making it so it doesn't reflect as much. These trees are perhaps shading only 10% of this array. But we're going to show you how that's bad, because when you shade the short edge of a module, you can actually take out the entire module, as we will learn in PV module fundamentals when we talk about bypass diodes. Now here is an IV curve and a power curve. The red line is the real IV curve, which should be nice and smooth, but the shadows on this IV curve are making it bounce down like this. We can see that the voltage is going up to 347, so perhaps there's 10 or so modules in series right there, and we're kicking in a bunch of bypass diodes. This is sort of like an EKG for a solar system, an IV curve. And so remember, current times voltage equals power. So we're showing you the power curve, and we're making peak power at about 190 volts. So if you have a maximum power point tracking inverter here, it would track the array right here. So your maximum power point tracking inverter would keep the array working at about 190 volts for maximum power, which would be right here on the IV curve. Remember, I is for current, V is for voltage, IV curve. And here we have it superimposed on a power and voltage curve. So this shading in this situation with this string inverter is making about half the power that it could have made if it was operating at the maximum power point without shading. This is an image from Solar Professional magazine. You can still go to solarprofessional.com and download all the old issues. It was really sad that they stopped making their magazine, but hey, I guess selling paper magazines was not the future. Go there though and download every issue that they ever made over 10 years. So somebody analyzing IV curves would be sort of like a solar doctor. This would be something that you would do for O&M. And once again, it's like an EKG, an electrocardiogram for solar. Some people can look at these IV curves and figure out exactly what's going on with a PV string. Some inverters even do IV curves from the inverter itself. Here's another image of a sun path. We're still on the slides that Solmetric gave me, and this is showing what they do. There's a tree blocking the sun, and they're using their special software to figure out how much solar energy you would lose, or to be more optimistic, how much you would keep. On the left is the old style Solmetric. I remember having one of these. And on the right is the current model, the 210. What we have here is a fisheye lens. Inside is an electronic bubble level. There's an inclinometer to measure tilt, and there's a compass. There's also usually a GPS in one of these things. You can use the GPS, or you can just pick your city. Up top is a bar graph telling you how much percentage of optimal solar energy you would get in the different months. There's picking the city in the middle, and they call this the skyline view. It's showing us that we're doing pretty darn good around summer solstice and just a few hours of sun around winter solstice. It's telling me here that my annual solar access is 85%. So that means that I would lose 15% of my energy. If I wanted to turn that into a derating factor I could do math with, I would call that 0.85. And then here we have our tilt, our azimuth, and our GPS coordinates. Latitude and longitude. So here's a guy up on a roof gathering data for the Solmetric. He wants to be where the solar is going to go, hold it level, and take a picture. So there's the bubble level that you would be watching, and you have to just point it close to south. If you're off by a little bit, the device can correct for you. They actually even have a pole, so if you don't want to climb on the roof, you could stick a pole up and get an idea of what you would do at a certain elevation. Solar Access does not derate for tilt and azimuth, and Solar Resource does for tilt and azimuth. If your software that you're using already derates for tilt and azimuth, then make sure to be using Solar Access. You don't want to double derate, or you'd be selling yourself short. So what we're doing here is figuring out how cutting down a tree would improve our solar access. Isn't that what we want to do? Cut down more trees for solar. Hey, save the planet, right? It's funny to me that sometimes your inverters will tell you how many trees you saved by installing a solar system because instead of using fossil fuels, somebody was using solar energy. So actually there is a math equation where you can save a bunch of trees by cutting down a tree so your solar system makes more energy. And this just really means that photovoltaics is more efficient than photosynthesis. Trees take CO2 out of the atmosphere and turn them into biomass. Fossil fuels burn old biomass, and PV prevents fossil fuels from being burned. Go figure. So the yellow paintbrush increases your production by getting rid of a tree or whatever shading something, and the green paintbrush, you would add a tree or a building. Also, if your sun was not in the right place, something would be wrong. So they took this picture within a few months of summer solstice in the morning. This would be summer solstice at noon. This would be winter solstice at noon, and afternoon is over here. Another neat thing about the Solmetric is with the GPS, you can take all of these pictures and it makes a Google Earth file. And then you can open it on Google Earth and it'll tell you where you were standing. A lot of times what happens is people go do all these site surveys and they thought they were going to remember where they were, and then they don't have a clue. It's also recommended to write down where you took each picture, but this is a really neat option to have, telling you where you were standing. So there's a guy, Peter, that used to work for Solmetric, taking a picture. Got our monthly solar access. Our annual is 86%. He can take the yellow paintbrush and get rid of that guy, and take the green paintbrush and paint in that part of the building that was reflecting so much light that the software thought that it wasn't a shadow. The Solmetric also makes a nice shading report that you can show your customers. One thing that happened with Solmetric a number of years ago is they got bought up by Vivint Solar. Vivint Solar is one of the top residential solar installers in the United States. Vivint Solar took the Solmetric off the market for a while, so most of their competitors had to scramble, and they figured out ways to calculate shading without the Solmetric. Some people think it might have been revenge. Not too long before, Solar City, which is now Tesla, was the #1 residential installer in the United States, and they bought ZEP, which was a railless racking company. Vivint was exclusively using ZEP, and then all of a sudden they couldn't use it anymore because Solar City bought ZEP for $158 million. I wish I would have came up with that idea. So then Vivint comes along and buys Solmetric, and now Solar City can't use it for a couple of years. So in the meantime, everybody figured out a different way of doing it. Then Vivint put the Solmetric back on the market, but it's not used widely like it used to be. It used to be that you had to have one of these things if you were getting financing for residential solar. So a lot of the big companies have their own proprietary shade analysis software, but if you have your own company, you might be using something like Aurora Solar if you're doing residential solar for shading. They do something that people like that's kind of neat called LiDAR. They use lasers to figure out shading. So this image here is giving shading information for this roof that's surrounded by all these trees and things. There's different places that there's LiDAR coverage. They had to have an airplane fly over with a laser in the different places. So you can see that it's a lot of the urban areas, places where a lot of the rooftop solar is in the United States. So that was Aurora Solar. And here we are looking close at the LiDAR. Pretty cool, huh? LiDAR. LiDAR stands for Light Detection and Ranging. It uses a pulsed laser to measure ranges. And here is the airplane flying over, getting some LiDAR data. I wonder if they've ever reflected any of these LiDAR lasers off the top of my head. Now we're going to talk about Helioscope. Helioscope is a competitor of Aurora. Aurora is more known for smaller systems, such as residential solar. Helioscope is more famous for commercial buildings and perhaps ground-mounted solar. Helioscope, you can also use LiDAR. A lot of times what people do, though, is they just draw the shading object. So if you're on a commercial rooftop, they might be drawing an air conditioner up there, which is pretty much a cube. This is a report from National Renewable Energy Labs, that's a United States government lab, validating Helioscope. Helioscope will also work with Energy Toolbase. Energy Toolbase is known for working with energy storage. So if you have a system with energy storage, you might want to look into Energy Toolbase. Energy Toolbase is also famous for analyzing data from many different utilities. There's so many different rate structures, time of use rates, tiered rates, and so many different utilities, thousands of them, that it's hard to keep track of. So if you want to figure out, will it pay to have an energy storage system, what size energy storage system, etc., you might want to be looking at Energy Toolbase. Energy Toolbase doesn't just work with Helioscope, it works alone, and it works with other software too. So if you're interested in this, I'd recommend going to their website and checking out all the things that they can do. Here's some analysis done by Energy Toolbase. They say it also can work with Aurora. And there's another software here too called Sighten, and they can do shade analysis. But if you want to play with the big boys, I'm talking multi-megawatts, it's almost required that you have to use PVSys for the banks to invest in these large projects. We're not talking rooftop here. We're talking big projects. However, PVSys can do rooftop, but that's not what it's known for. They have simple drawings and they have output data that is super analyzed. Plus, they've just been around for a long time, so the banks are used to it. Even if you came up with software that was better than PVSys, it would be very difficult to get people to use your software. Here's an independent company called Albedo. Remember, that means reflection. And what they're doing is they're doing PVSys for you because it can be difficult to use. So there's different companies that you can hire to do the PVSys analysis. And as I was saying, purchasing and financing entities such as banks, utilities, and private power purchase agreement stakeholders often require PVSys modeling as a critical part of ongoing negotiations. Somebody watching this video might learn PVSys and get a good job doing PVSys. And the best way to learn about software is from the software company. So PVSys does training in Geneva, Switzerland. What a great excuse to go to Europe. Their price is about $2,300 for 4 days. That means a Swiss franc is pretty much about $1. So how are you going to render your project? How are you going to design it? How are you going to make electrical drawings? There's different kinds of CAD programs. CAD means computer assisted drawing. This particular CAD program is called SketchUp. SketchUp is kind of famous. It used to be made by Google. However, Google sold it to a company called Trimble quite a while ago. They have free versions, they have paid versions. You can learn it on YouTube, but it does have a learning curve. They have a warehouse where you can pull out a solar array and change it. Solar modules, solar inverters, wires, conduit, junction boxes. You can get as detailed as you want with these CAD drawings. And then here we have a company called Skelion, which is a plug-in for SketchUp. That means it works with SketchUp. You pay them, and it does extra stuff. And it's made just for PV. So we can see here that it works with SketchUp, Google Earth, PVGIS, PVSys, and PV Watts. I wish that was my house. Here's something I thought that was kind of neat with Skelion. So you can see some of the different things that you can do rendering a PV system. Look at those shadows. That right there is not even PV. That's called a parabolic trough. That's a solar thermal thing. Here's a CAD program that's only for PV. It's called PVCAD, made by PV Complete. Funny thing is when I was learning AutoCAD about 12 years ago, I purchased pvcad.com. So if you want to find out about PVCAD, you have to go to pvcomplete.com. And they make a CAD program that's specifically for solar, and they're cool. They're in Oakland. Now, the industry standard for all drawing, for all architects, for big projects, is called AutoCAD. If you're big time, you're using AutoCAD. It's made by Autodesk, and the people that do this can have a whole career at it. But they could build things quick. I imagine somebody that's good at AutoCAD could have built this whole thing in less than an hour. Probably a lot less than that, really, if they're really good. So we see a PV array on a slope. So if you wanted to get into drafting, learn about AutoCAD. Most community colleges have AutoCAD courses. It's a good thing to know. This is from a permit package that I hired somebody to make for a job that I was doing. We put PV facing on every direction. We're actually going to just install these two roof faces, but one of the things that I like to do is put solar everywhere and then subtract. It's kind of easy once you put on a solar array to just flip it over, put it here, put it there, put it there. So that's AutoCAD. So all of this software, what's the best way to learn how to use the software? From the software company. or maybe a community college course if it's something that's so big time like AutoCAD. But especially the solar design software, it's really good to learn from the company because they have every incentive in the world to get you hooked on their software. There's a big learning curve for all these different softwares. So it's not like you're going to just learn one and then switch all the time. And who knows the software better than the people that make the software? Most software companies have free training. It was just PVSys where you have to pay a whole bunch of francs. And if you want somebody to do layouts and permit packages for you, here's a number of different companies that make solar permits. And there's a whole bunch more besides these companies. It's pretty easy just to go out there and do a search for solar permit companies, or you can try one of these here. A little bit about interrow shading. One of the easier ways of doing things is you just have a ratio. So you could go 2:1, 3:1, 2.5:1. One of the things that I did before is I found some rooftop racking systems that already had it built in, and I did the calculation, and I found that a lot of them were doing 2.5:1. The further north you go, the longer you would want this space to be, the interrow space. In my advanced class, I go through the trigonometry calculations of how somebody might calculate interrow spacing for different latitudes. But here, I'll just kind of tell you what trig is and not expect anybody to do trig, especially for the PVA exam. If you know two things about a right triangle, then you can figure out everything else about that triangle. Here we would know the elevation of the sun. Say we would want to be shade-free by 9 in the morning. So that would be the solar elevation angle. You can get that from one of those sun charts that we were looking at. We would also know the tilt angle of the module, and we would know the length of the module or the array. So if I know the length of the module and the tilt angle, that's two things about a right triangle. Right triangle means 90 degrees. Then I can figure out the height. Then if I know the height and I know the sun angle, that's two things about this right triangle. Then I can figure out the distance. However, if that was at 9 in the morning, here's 9 in the morning, I would also have to figure out the difference in azimuth from 9 in the morning until noon and do another trigonometry calculation, because from my previous slide, I had the distance being here at 9 in the morning, and this is my distance at noon for my array facing south. So I know the length of this side of the triangle and that angle right there. So then I could figure out this interrow space. If you are interested in relearning trig or learning trig, you can even go to Wikipedia and figure it out there. This is an old website that I made, and I have an interrow spacing calculator right here. It's an Excel spreadsheet, and if you want to, you could use that, punch in some numbers, and it does all the trig for you. Let's talk about the solar energy fundamentals of this system, which is called a single axis tracker. It's a horizontal axis. It points at the sun in the morning, it points in the sun at the afternoon, and at noontime, unless the sun would be straight over your head, it's not pointing at the sun. It's actually flat at noon. They can put a whole bunch of PV on one tracker, and when the PV system is big enough, it will pay to do maintenance on a system like this because you will get extra energy. And another reason why utilities and solar energy producers like these types of systems is it doesn't make all the energy just at a big peak at noon. It makes extra energy in the afternoons. You can see this system right now, it's almost flat, so it's about solar noon, and it's not facing the sun because we are doing detective work by looking at these shadows. So if we're in the northern hemisphere, then south would be the direction to the left of these posts. But maybe that's Mars, it is red soil. This is kind of a famous picture of a concentrated solar array. Concentrated PV needs to track the sun all the time. We have special lenses and perhaps mirrors inside of here reflecting and focusing the light onto a super efficient, perhaps gallium arsenide, 30% efficient solar cell. When PV was a lot more expensive, this made more sense, but nobody does this anymore. You can see how old this picture is because that was the first Tesla there ever was. That was a Roadster. In fact, I remember test driving one of these cars in about 2010 or 2011, and it was that same color. Maybe that was the car I was driving. But man, did it take off like a rocket. This is a concentrated PV system that I drive by a lot. It's on a bridge called the Dumbarton Bridge in the Southern Bay Area, if you're ever there. And one of the things that I notice about this is these trackers, they don't aim in the same direction most of the time. They're aiming in different directions. That means that this is not working because concentrated PV needs to focus and aim straight at the light. If you had regular PV and your tracker broke, you'd still be getting production. With concentrated PV, you would very rarely get any production because you need to focus those light beams. Concentrated PV is neat, but it's just not common anymore. We've talked about this, and let's talk about it again. This is something that you're likely to see on a NABCEP associate exam. These are called rules of thumb, different ways to point your PV to optimize for different seasons. One of the things that I always thought that was interesting, that the sun paths in the fall and the winter are almost exactly the same. And the sun paths in the summer and the spring are almost exactly the same. That's because the shortest day of the year is the first day of winter, and then the days start getting longer. And the longest day of the year is the first day of summer, and the days start getting shorter. Go figure. I think summer is hotter than spring just because Earth has been warmed up for a while. And the same goes with winter being colder than fall because fall has cooled off that part of the Earth for a while. So these rules of thumb have to do with how we tilt our modules. Let's look right in the middle here. For annual tilt, the best production is generally about a latitude tilt, or for most of the continental United States, more of the temperate latitudes throughout the world, 30 degrees is pretty good. It used to be on the associate exam, the right answer was latitude tilt, but then they swapped it out for 30 degrees. So if you see latitude or 30 degrees, that's best for annual production. A lot of times people tilt less than optimal because there's different benefits, such as you can fit more PV and there's less wind uplifting issues. However, for maximum production, from a PV module, latitude tilt or 30 degrees tilt is pretty darn good. To optimize for winter or fall, you would perhaps tilt at latitude plus 15 degrees. So if you were at 30 degrees latitude and you were designing an off-grid system, to optimize for winter, because that's going to be your critical design time, your critical design month is going to be that month with the worst production. So it's really common with an off-grid system. People try to optimize for the worst time of the year, and they will tilt something at latitude plus 15. So if you were at a 30 degree latitude, that would be 30 plus 15. That would be a 45 degree tilt. These rules of thumb do not work everywhere because if you're at the North Pole with a 90 degree latitude, would you really be tilting it 15 degrees towards the ground? Or should I say ice? Now, to optimize for summer or spring, they would say to tilt it at latitude minus 15 degrees. So that means if you were at 30 degree latitude minus 15 degree latitude, that would be a 15 degree tilt. If you're putting solar on your roof, you just go with the slope of the roof. When PV was more expensive, people would tilt it up on their roofs. Now, if you tilted it up on your roof, people would laugh at you. I thought this was interesting when I was getting my pilot's license. 1 degree latitude is about 69 statute miles. That's 111 kilometers, and that would be 1 nautical mile. Degrees latitude are pretty close to being the same from the North Pole to the South Pole. But longitude degrees are very different as you go further north from the equator. If you were at the North Pole, you could walk 360 degrees latitude in a minute. You would have to approach the speed of light to be able to do that at the equator. Another thing that's interesting is degrees and latitude are divided into minutes. So 1 minute of latitude is 1 nautical mile. The Earth also is a little bit wide at the waist because of that spin, so that's why it's not exact. Because did you know that the Earth wasn't round? Don't worry, I'm not trying to start a flat earther conspiracy theory, but I'm just saying, as something spins, its waist gets wider. Like, look at Saturn's rings. You weigh a little bit less at the equator than you do at the poles because that spin is lifting you up a little bit. This is where we're going to meet. These are the big solar conferences. We have SPI, that's also known as Solar Power International. It's sponsored by SEIA, who also has different regional conferences. SPI is typically in the fall in the western part of the United States. Lots of people and lots of stuff to see at these big solar conferences. We also have Intersolar US, and there's Intersolar conferences all around the world. Intersolar US, lately, has been in California in the winter. Intersolar Germany, which I go to every year, is going to be spring or summer in Munich. Great reason to go see my friends. Then there's the American Solar Energy Society. I'm on the board of directors of a division of ACES called NorCal Solar. ACES is really the oldest solar organization in the world. ACES is also closely related to ISIS. That's the International Solar Energy Society. And yes, they didn't want to change their name because of those bad guys. So they're still called ISIS, but it's ISES. So I'm closely connected to ACES. ACES conferences used to be a lot bigger, but hey, these trade shows compete with each other. They're very competitive. SPI also teams up with SNEC. I'm good friends with the owner of SNEC, and she gets 260,000 people to turn out every year in Shanghai in about May or June. I also teach a National Electrical Code workshop at SPI, at Intersolar. I teach classes at the ACES conference, and I teach a class at the SNEC conference. So you can also go there and take my class. We talked a little bit about software. Here's just some other software if you feel like going down the list. A lot of this we've covered, some of it we haven't. I recommend just going to their websites. That brings us to the very end of Solar Energy Fundamentals. Take a breath, take a break, absorb that information into your brain, and get ready for the next lesson.